Welcome everyone. So this is our 47th live stream geometry. So we have me and 4 other people with us so far, and a couple new people this time, which is nice to see. And today I'm going to go over the Taiwan team selection test. So I did some problems in the past from the Taiwan IMO training, but I don't think I've done the team selection test, and they have a lot of nice problems. So with that, I'm going to get started. So let me share my screen.
Hello, Michael.
Hi, Dat. Thanks for joining.
Yeah, nice to see you.
You too.
Michael, I have some problem that I could share you. This is Vietnamese training from the years of 2017.
Okay.
Kind of difficult. I mean, yeah. If you want, I could share on the Discord.
On the Discord? Yeah, send it on the Discord. Yeah, maybe if we finish the others, we could do that in the end.
Okay.
Thanks. So where did you say you got it from?
From Vietnam, IMO training of Vietnam.
Ah, sounds good. Yeah, I'm looking forward to seeing it. So, all right, so I'll get started with the first problem. So we have a triangle ABC with circumcircle gamma. And E and F, this is interesting. E and F are any points on side CA and AB. So that gives us like a lot of flexibility. So this E and F can be any 2 points. I'm going to delete that. So the circumcircle of, looks like we have another person joining, Quan. So the circumcircle of AEF intersects the circumcircle of gamma at point X. Hi, Quan. Thanks for joining. So this right here is point X. And so it looks kind of like a spiral similarity problem, right? So triangle XEF is similar to triangle XCB. The circumcircles of ABE and ACF intersect at K. All right. So Quan, where are you from? I don't think I've seen you before. Okay, so this is point K right here. And AK intersects the circle again at M. I want this thing to go away. It'll go away. There we go. So that's M. And let N be the reflection of M over BC. I have to wait for this thing to go away. There we go. So this is point N. I'm going to move the diagram up a little bit. XN intersects the circle again at S. And we want to show that SM is parallel to BC. This looks a lot like a problem that we did recently, I feel like, but I forgot the solution to that. Let me move the diagram up a little bit. All right. So I will hide a couple things just to make it look better. And let me see. I'm going to draw segment NM. So BNCM is a kite. So yeah, we'll have to figure out how to use that. Okay, so is S, I don't think S is the antipode of A. Let's see, so if I, No, that's not a right angle. So yeah, it's interesting how much flexibility there is here. E and F can be any points. X is the McKell point of BFEC. Yeah, exactly. So yeah, X is the McKell point of BFEC. And a spiral similarity means that triangle XFE is similar to triangle XBC. And you can also see that by an angle chase. Because angle XFE is 180 minus XAE, and which is 180 minus XAC, which is XBC. So yeah, it's easy to see triangle XFE is similar to XBC. There's a couple similar triangles actually. So yeah, XFB is similar to XEC also. So I guess if we want to show SM as parallel to BC, we could try to show that angle BAM is angle SAC. That's one way to do it. So, and BAM is BAK. That's interesting. I don't know if it's worth drawing this point right here. Let's draw it anyways. I wonder if it's worth letting AX intersect BC. Then maybe we could like use projective geometry somehow. Not sure. So basically we want to show AM and AS are isogonal. Maybe we could use the isogonal line lemma somehow. So I'm going to let AX intersect BC. Not even sure, it just feels like it might be useful, but I'm not sure exactly how. I wonder if there's a, so we can also try to show angle AXN is equal to angle ACM.
Or maybe we can start by drawing the line parallel to BC up to M. And
M.
let it intersect gamma with.
All right, N. Sounds good. So basically I draw the line through M parallel to BC, and I let it intersect gamma at S prime. And I want to show S prime is equal to S. I like that.
Yeah.
And so, yeah, we want to show X, N, and S prime are collinear. And Irajan just said that G, F, and E are collinear. Is that using like projective geometry, or is that that's just a radical axis theorem? I'm trying to think. Just by radical axis theorem. Okay, so we have this circle, and then we have the circumcircle of ABC, And then we don't know no, GF and E are not collinear because BFEC is not cyclic. That would only be true if BFEC was cyclic. I saw Serdar just joined. Thanks for joining. Okay, so we want to show angle, yeah, only if BFEC is cyclic. We want to show angle AXN is equal to angle ACM.
Actually, I think we can say that NS prime goes through the midpoint of BC.
Oh, really? Oh, yeah, because that's a good point. So yeah, NS prime passes through the midpoint of BC by symmetry.
Michael, I think if we prove XM is the symmedian of triangle XBC, then we will solve the problem.
Oh, really? So XN is the symmedian?
No, XM.
Oh, XM. All right.
And then XN will be the median.
Okay, interesting.
If we could prove XM is the symmedian. So when we reflect M over BC, then XN will be the median, and that will solve the problem.
I think that, and isn't I think Serdar might have mentioned before, isn't there like some lemma that says that XM is a symmedian?
We could prove this because we need XMBC is a harmonic quadrilateral, which means we need XB over XC equal to MB over MC, right?
Yeah.
Okay, so after that, we will use the sign. So XB over XC is equal to FB over EC.
XB over XC, sorry, XB over XC is, did you say is EB over E, or?
FB over EC, spiral similarity.
FB over EC, yeah.
Yeah, and MB over MC is sine angle MBAN over sine angle CAN. Which is angle FAK and over sine, which is sine angle FAK over angle sine angle CAK, which is FK over CK.
Okay, let me write out some of this. So we want to show ABMC is a harmonic quadrilateral, and then that'll prove that, I'm sorry, XBMC, and so then XM would be a symmedian. Okay, so let's see. Hold on just a second. So we have XB over XC is FB over EC. So by a spiral similarity at X, so XFB is similar to XEC. And so XB over XC is FB over EC. And FB over EC, and then you said BM over MC that's sine of BAM over sine CAM. That's what you said, right?
Yeah,
And which,
yes.
and that's sine.
No. I think we should prove triangle BFK is similar to triangle ECK.
Okay.
That is because angle BFK is equal to angle ACK, which is angle ECK.
BFK is ACK, which is ECK. Okay.
Yeah. And CEK. Yeah.
Hold on one sec. Let me write that out. BFK is AFK. BFK is ACK, which is ECK.
Yeah.
Yeah, sorry, it covers up the diagram. So so we want to show so FB over EC is X.
No. In angle CEK is equal to angle ABK, which is angle FBK.
Okay, so CEK. Hold on, is this right here? So
no. That is that is ECK. That's correct. But I say the another
okay.
CEK.
CEK.
Yeah. CEK is equal to ABK.
ABK.
Yeah, and that is FBK. So, which means that two triangle is similar.
So BFK is similar to CEK.
BFK is similar to ECK.
Okay, so those triangles are similar.
Yeah. So FB over EC is equal to FK over CK.
Okay. K over CK. And so then we could set these equal. So why is BFK? So BFK is equal to ACK because AFKC is cyclic. Vance just asked me. Oh, because AFKC is cyclic. And so in a cyclic quadrilateral, basically ACK is 180 minus AFK, and that's the same as BFK. Okay, so then we can set these equal. So XB over XC is equal to FK over CK.
Yeah, and FK over CK is sine angle FAK over sine angle CAK.
Okay. Sine FAK over sine CAK.
Yeah.
And that's equal to BM over CM, right?
Yes.
So I'll just write out that one more step. So sine BAM over sine CAM, which is BM over CM. Okay, so we have all that. Let's see if it, that's nice, it all fits. So combining the above, XB over XC equals BM over CM. That means that XBMC is harmonic. And that implies that XM is a symmedian of XBMC. BMC. And so that implies that XN is a median of I'm sorry, this should just be XBC. All right, so, okay. So XM is a symmedian, and then from there it's well known that XN is a median of that triangle. And so from there, if basically that means, I mean, that basically solves the problem, because then we know angle XBM is equal to angle CXS. So I'm going to rename this S just for now. Well, but yeah, we did need to know, let me think how to phrase this. So yeah, oops, sorry. I mean, maybe it is worth leaving it as S prime, because well, actually, no, all we need is, so yeah, so I'm going to rename it as S. So basically, so XM is a median and XN is a symmedian. So that means angle BXM is CXS. Whoops, sorry about that.
You can just say this is a well-known property.
Yeah. So yeah, so this is well known, but that implies angle BXM is equal to angle CXS, and that implies SM is parallel to BC. All right, so that is that. It all fits on the page. I like that. So I will move on to the next one. So thanks everyone for your help. This looks hard. So I'll see. I think this was like problem 6. I'm not really sure how hard it is, because it's like a simple problem, but it's like an interesting question. So we have a rhombus. I haven't done too many problems on my channel with like a rhombus. So how do you draw a rhombus? Let's see. I think I could just, I'm going to reflect B across AC. I think that's a good way to draw it. And O is the center. So this should be point D. And O is the center of the rhombus. And P is any point on AB. Call this P. And then we draw the incenters of PCD, PAD, and PBC. So I'm going to draw the end circles. Hold on 1 second. Okay, so we have a end circle of PCD. Then we have the incircle of PAD. And then we have the incircle of PBC. And we want the centers. So actually the circles are C. I'm just going to do it this way. So might have to rename them. So draw the three centers, I, J, and L. So E lies on by symmetry. So for PAD, it's J, and PBC, it's L. So those lie on the diagonals of the rhombus by symmetry. And this one is I. And then we draw the orthocenters of PLB and PJA. So let me see. So H is the orthocenter of PLB. That's H. And K is the orthocenter of PJA. And we want to show HK is perpendicular to OI. Let me hide the circle. It's kind of silly. Let me see what if I can make anything bigger. Kind of like that. But it almost looks like K lies on the circle. So
you can move A.
I can move A. Yeah. So maybe that looks a little better. So K is the orthocenter of, or J is the orthocenter of AKP, and L is the orthocenter of PHB, because we can flip the orthocenters that way. So I wonder if maybe we could show IK squared minus OK squared is IH squared minus OH squared. I don't know. Yeah, it's a very symmetrical problem. Maybe I don't know if this is drawing too much, but yeah, it just, to me, so yeah, I can see J is the orthocenter here. So, I mean, if J is the orthocenter, then we can draw this point. So KP is parallel to BD. And PH is parallel to AC. Or did I say that right? We actually have a rectangle here, OEP, like I should draw that other point. So I can move A. Yeah, I'm not going to be able to get like a perfect diagram, but I could draw this point right here. So let's see. It's GeoGebra is making it difficult to label it. Come on, trying to get the intersection. Come on. It doesn't want to do the intersection. Okay, let's see. I'll just make it, sorry about this. I'm just going to make it really big. There we go. So OEPF is a rectangle. Sorry. Maybe it's worth just also drawing these points. So K, J, and G are collinear, and H, L, and M are collinear.
Can you draw the incircle of A, B, C, D?
Oh, the incircle of the rhombus?
Yeah.
Yeah. Just a second.
Maybe we can use radical axis.
That would be interesting. Okay, let me hide some stuff. I see someone wrote something in the chat. Hold on just a second. Why is OEPF a rectangle? So basically, we know angle EOF is a right angle because the diagonals of a rhombus are perpendicular. And we also know that angle K, we also know that angle, we also know that EP is parallel to BD because EP is perpendicular to AJ, and so is BD. So we know that this is a right angle, EOF, and then we know that KP is parallel to BD, and then we know that PH is parallel to AC. So that's why EPFO is a rectangle. So yeah, that's interesting. So yeah, O is the center of this circle, and I is the center of that circle. And we have a bunch of homotheties, right? A homothety at A takes this circle to this circle. Maybe we could even use Monge's theorem because A is the intersection of the common tangents of these two, and B is the intersection of the common tangents of those two. So
are the tangency points same? The O and I.
O and I, no, I think there's another intersection point here. Yeah. Oh, but you mean the tangency to this? No, I don't think they can be because tangency from O would be perpendicular, and the same with I. So yeah, they don't have the same tangency point. I'm drinking a red tea right now. Do they have, I think I heard in Turkey they drink a lot of tea. Is that true?
Yeah.
Yeah.
Every evening.
And isn't their tea also like a red tea?
It's kind of black, I think. We also drink it much.
Okay. Interesting. So OI. Let's see. But yeah, this was number 6 on the team selection test, and it was proposed by Buratino. You guys know Buratino? So
yeah.
He's like a math. He has a lot of really, really hard problems. So I don't know.
He really, yeah.
I don't know how
He
hard.
has a website.
A what? I'm sorry.
He has a website.
Yeah. All right. Is O the orthocenter of IKH? Probably not, but maybe. That would be interesting. Let me try that. I would be very surprised if that were true. Yeah, no, that's not. Check the chat. Yeah, I was thinking about Monge's theorem. So, but the thing is, I think Monge's theorem would be kind of trivial. Well, so these three circles all have AB as a common tangent. So that kind of makes it less useful. But yeah, I don't know. Maybe there's a different way to use it. Okay. But which circles would we want the insimilus, like?
J and I and L.
Oh. So, for example, whoops. Oh, like this point right here?
Yeah, that one.
Okay.
Three circles have the same tangent. You
Yeah.
draw that again? What you draw?
Yeah, it draws too many tangents, but I can hide the rest.
So one of them is.
Whoops, sorry.
Middle one is.
Let me hide this and this. Is OI and the tangency point collinear? Let me check. That's a good idea.
One of the tangents is mutual.
Yeah, no, OI doesn't pass through the tangency because like you'd have to draw the perpendicular from O to the tangent to get to the tangency point, and for I you'd also have to draw, yeah. Yeah, let me draw these points.
Three circles have a common tangent.
Yeah, so this is a common tangent, right?
Is this trivial?
Is it trivial, or is what trivial? Oh, that they all have a common tangent. Yeah, that is a good observation. That's interesting. I'm not sure.
Actually, this is not trivial.
That's surprising. Whoops, sorry. Should be us.
Actually, OD is perpendicular to PH and OC is perpendicular to PK.
Yes.
So if we want to show IO is perpendicular to KH, then maybe there is a connection between PKH and DIC.
Also, triangles PKH and ICD should be orthologic.
PKH and ICD?
Yes, because since we have the perpendicular from C, the perpendicular from B, and we should have the perpendicular from E, which goes through O.
Yes, that's what I was trying to say.
So these two triangles should be orthologic. If we prove that, then you're done, basically.
All right, nice. Good observation, Melek. Yeah. And thanks, John. So we want to show they're orthologic. All right, PKH and CID. So
then we can show that they are orthologic if the perpendicular from P to CD and the perpendicular from H to the line DI and the perpendicular from K to line CI or concurrent.
So let's draw those. So P to CD, and then K to, is it DI? Or I think it should be DI.
The other one.
Oh,
K
CI?
to IC. Yeah.
K to IC.
Yes.
Okay. And then H
to IB.
Interesting. So
If
we can
show that, then the triangles are orthologic, which means we are done.
All right. So, okay. So CI and DI, those are the angle bisectors in triangle PCD, right? I don't think I've ever used orthologic triangles before on my channel. So this would be cool if it was the first time. I'm just going to draw that point for now. Call it U. Whoops, sorry. So if we can show that PU, and so this is the perpendicular from K to CI, so maybe I should extend CI. Extend DI. So these are like the perpendiculars. Yeah, let me extend this also. So just draw on those points. So this point, we're already up to W. We've drawn that many points. Okay. So all right. CIV. If we show H, is HK, no, HK is not parallel to AB. So yeah, really we have to show point U exists. Like if we can show that, that's one way of solving it. So yeah, we can basically define K as the intersection of of the perpendiculars at G to AB and the perpendicular at P to AC. But yeah, the fact that these three circles all have a common tangent is really interesting too. Yeah, I'm not sure if, yeah, I don't know if the orthologic, how much that helps, but it's interesting. So yeah, it doesn't seem at all obvious that all three circles have a common tangent. I wonder if there's something special.
Did you know a film which called Monty Amber?
Monge de Alembert. Yeah, Monge's
Yeah.
theorem. Yeah.
Yeah. So that will prove the three circle have the common tangent.
That would prove it.
Yeah. So if you call the tangent, the common tangent of the circle J and L.
Okay, so this one, so the common external tangent, right?
Yeah.
Whoops, sorry, I didn't draw that right. Yeah, sorry, I'm trying to make it a good diagram. Let's just shrink it a little bit. Sorry. So yeah, so this point over here, right? So that's point Z, right?
Yeah.
And then, so you said you could prove that they all have a common tangent, right?
Oh no. Just let me think again. Yeah.
Okay. No worries. I'm just gonna erase that for now, just to make the diagram easier. So let's check the chat. Can we find some line parallel to IB? Let's see. So it's the angle bisector of PDC. But the thing is, we can just define the, well, yeah, so Vance just asked me. So yeah, KG is parallel to HM because both are perpendicular to AB. Yeah. Yeah, that's interesting. They all have a common tangent. PJ is parallel to IB. Maybe it is. Let's see. All right, we have one more person that just entered. I think it's Daniel. So let me see, PJ and ID. Let me check if they're parallel. So what's the best way to do that? So if we could show that the angle APJ is DC. So so PJ and ID are parallel. Yeah, you're right. That is a good observation. So the perpendicular from so yeah, if we're just thinking about orthologic, the perpendicular from H to ID is the same as the perpendicular from H to PJ. Yeah, and now we can get rid of I. No, I actually really like that. So, so we have a perpendicular here, and then we also have a perpendicular here. So we want to show yeah, we can get rid of I. We could show the perpendicular from K to LP and the perpendicular from H to PJ, and the perpendicular from P to AB are concur. So it's almost like we have another two orthologic triangles, right? So yeah, I wonder if I draw this intersection point and this intersection point, then basically P is the orthocenter of that triangle. So P is the orthocenter. We want to show, no, P is the orthocenter of A1ZU. This is really interesting. Wait, does that solve it? I wonder if we've solved the problem. Because, well, we don't know point U exists. That's the problem. But I think if we can show A1Z is parallel to AB, then that would solve it. So I can hide a few things then. So basically, yeah, we want to show A1Z is parallel to AB. That would solve the problem. Whoops, sorry. You don't think we should hide U? Okay, I could add it back. But basically, so A1 is the intersection of PL and the perpendicular from H to PZ, and then, or H to PJ. And then Z is the intersection of PJ and the perpendicular from K to PL. So we draw the perpendicular from K to PL. We draw the perpendicular from L to PK. And we let those intersect at Z and A. And we want to show, why is it enough to show it's parallel? Because if it is, if ZA1 is parallel, then but basically, suppose I just let U be the intersection of these two. So suppose I define U that way. If I could show ZA1 is parallel to AB, then that means P is the orthocenter of UA1Z. And so that would mean UP is perpendicular to AB. And then we could use the orthologic triangles that you and Melek mentioned, and that would solve it.
So we want to show ZPA1 is similar to DIC, right? Because we already have the two sides are parallel.
Yes. So yeah, if we could show they're similar, that would solve it. That's a good observation.
How could we define A1?
A1 is the intersection of PL and the perpendicular from H to PJ.
Oh, okay.
So one second, guys, I'll be right back. All right, thanks for waiting.
I think I solved it.
Okay. How did you solve it?
I basically calculate the IC, the angle DIC, and JPL.
Okay, BIC and JPL.
Yeah, and it turns out that they're equal. So we have JP parallel to DI and LP parallel to CI.
And then did you use ratios? Like, did you show PL over?
Oh, I see. Yeah, I'm not actually finished it now.
Okay, keep going.
Yeah, sorry.
It's all right. So yeah, if we can show that PZ over PA1 is equal to DI over IC, that would solve it. AK, do you mean parallel to UH? Yeah, AK is parallel to UH because they're both perpendicular to PJ. We want to prove UP is perpendicular to AB. That would solve the problem. And if we can show, well, so how would we define U? So we could draw the perpendicular at P. Yeah. HPU and AKJ are similar. Let's see. Interesting. Because we have all those parallels. Interesting. Maybe we could even use. So yeah, if you look at AKJ and HPU, the sides would be mutually parallel if the problem were true. So wait, can we show, so we have triangle AKJ. So if we drew the perpendicular from P and we let it intersect H, we let it intersect this line, so the perpendicular from H to PJ at like a U prime, then yeah, then HPU prime would be similar to AKJ. And then we could say like KPU double prime would be similar to BHL. And then if we could show those two are equal. So yeah, so we would want to show, so we would have PU prime over HP would be equal to KJ over AK. And then I kind of like that. So actually, yeah. So let me write this out on a piece of paper. So, because I think this idea might work. So we have PU prime over HP is equal to KJ over AK. And then we have PU double prime over KP. is equal to HL over BH. Okay, so yeah, AKJ and BLH. So here's what we want to show. If we could show this, it would solve the problem. KJ over AJ. You might be right. KJ. Yeah, you're right. KJ over AJ. So HL over BL. Yeah. So if we can show this, so then it would solve the problem. So we want to show HP times KJ over AJ is equal to KP times HL over BL. If we could show that, I think that would solve it. Oops. Sorry. Why won't it work? There we go. So yeah, see if any of you can prove this. So HP so can we say anything about HP over HL? Because there's like a lot of, let's see. So yeah, this looks like it might be reasonable. Yeah, H is the orthocenter. So yeah, we would have, maybe it's better to write this as, do we know pH? pH times LB. I think we know that, yeah, what would pH times LB represent? So another way of saying it is, it might be easier to put all the stuff for each triangle on one side. So pH times LB over HL. So this is the same as pH times BL over HL is equal to PK times AJ over KJ. Yeah, so in this way, all three of these are from the same triangle, and the same with these three. Maybe that makes it easier. So you LB in terms of pH. Yeah, it feels. So I know that like BF times LF is PF times FH. But yeah, I don't know this right here. So BLM is similar to BFLH. I'm not sure how much that helps. BMH is, I'm just trying to find all the similar triangles. So yeah, this seems like it should all be computable, right? All these sides. I just don't know where to start. So we have, I think I have one idea. So we have pH over PM is equal to BL over BM. But we want pH times BL. That's the thing. No, it would be BL over LM, sorry. pH. Hey, Amal, thanks for joining us. So yeah, this looks like a really hard problem, but we've made a lot of progress on it. LB is 2 cosine A. 2 cosine A times what? Oh, where R is the radius of this circle. Let me write this. So pH over PM is equal to BH over HM. And pH over HM is equal to BL over LM. BL over BM. Over HL. I'm writing something out on my paper. HL. Oh, you just sent it on Discord? Hold on 1 second. Let me see. So HA is 2R cos A, HD is 2R cos B cos C, and EF is A cos A. All right, I'm gonna draw it. All right, I'm gonna go back. Sorry. AJ over KJ. That's HM times BL squared over HL times BM. So I'll spend like 10 more minutes on this one, and then maybe we can move on to the next one. Let me make sure this is actually right. PU prime. I think that's right. Show over BL. Yeah, I'm pretty sure this is right here.
If we have this, so how can we solve the problem?
If we know that this is true, or do you know of a way to show that this is true?
No. I think I might have. So if you if you calculate PL, oh no, oh you want PH, PH over LH. Oh, okay. So you want a PH over LH, which is sine of PLH over sine of H PL, right? And we have that sine of, and we have angle HPL.
Sine of HPL?
No, and we have angle HPL is equal to angle HBD, right?
Yes.
And but HP is perpendicular to PL. And so HP will be perpendicular to IC, right?
IC.
Yeah.
HP is perpendicular to IC.
Yeah.
So basically, do you think you could prove this using similar triangles or trigonometry?
Just use the sine theorem.
The sine theorem. Okay.
But if we have this, so how can we prove the problem?
Oh, so yeah, it's a long. So I could explain it after, but I'm gonna write it up. But okay, so Irajan, you just wrote PH times LB is sine 2A.
No. Hold up. Let me take note. I want to make sure my proof is correct. Yeah.
Okay.
Okay.
Actually, if we can find JKP is similar to JAD, then it's finished the problem too.
Did you say JKP is similar to JAD?
Yes, but I couldn't prove it yet.
Let me check that. That's interesting. Okay. Okay, so that formula should all right, see you later, John. So did you say JKP and JAD?
Yes.
All right. Interesting.
If we find it, then similarly we're gonna find P, H, L, and I don't know. Then it's the ratios are gonna be equal because one of them is gonna be AD and the other one is gonna be equal to BC. So we basically finished the problem.
So like you didn't use this, you solved it a different way, right?
No, I used that.
Oh, you use this. Okay. Interesting. Yeah, maybe there's a way just to do it like that. Let's see. Because yeah, I can show that this angle is this angle, but yeah, the other yeah, I want to show that this angle is equal to ADJ. Oh, I think actually it's not that, because angle ADJ is half of angle APD.
Michael. I could prove it. So let me say it. So HB over HL is equal to sine PLN over sine LCB.
Okay.
So we have that angle LPH is equal to angle is equal to angle LBH is equal to angle OCI, and OCI is equal to BCL.
BCL.
Yeah. So HB over HL is equal to sine of PLH over sine HBL.
PLH over HBL.
Yeah, and PLH is PLM, right?
Mm-hmm.
Yeah, and HBL is LCB.
Okay.
Oh no, you just I think you need to write up.
Yeah, I'm gonna write up some stuff. Yeah, I think that would make it easier. But I think what you did might be sort of equivalent to what Melek was saying. I think so I think Melek might have done the same idea, but without trigonometry. So like, because I think I can prove that. So JDA is half of ADP, and
I actually proved that.
You proved it. Yeah.
Yeah.
Okay. Hold on one sec. Let me. So first, let me write everything up to this point. So, JPB1. Sorry. So here's kind of how okay. So I'm gonna say let okay, so we want to show that CID and HPJ are orthologic. So that means this so the perpendiculars from each vertex to the corresponding side of the other triangles, corresponding sides of the other triangles concur. Okay, that's what orthologic means. Dat. Here's kind of, I'm just writing out how we got to that equation. So we have that. I'm sorry, not CID and HPJ. CID and I think it was H. Was it OJ? I forgot. CID.
Or that is HPJ.
It is HPJ.
Yeah.
Because HP.
HPK, not HPJ.
HPK. Because
CO is perpendicular to BK and DO is perpendicular to PH.
Yeah. Okay. So basically, we know that PH is parallel to CI and PJ is parallel to ID. So so that's kind of an angle chase. And PK is I'll just say that's true by an angle chase. I'll just say, so basically let you, so I'll say, let the perpendicular, so let the perpendicular from P to AB meet the perpendicular from H.
अगर मैं नहीं दूं अगर मैं एवरेज दूं 0.46 तक मैं पहुंच जाऊंगा 0.48 के बाद क्या 0.48 के बाद क्या है तीसरा डिजिट
So the perpendicular from
4% काफी है
to PJ.
5 से नीचे आएगी ना we are good
Anmol, can you put yourself on mute? Sorry. I'm just going to mute him for now. Okay. Sorry. At U prime, and then let the perpendicular from P to AB meet the perpendicular from K to PH. U double prime, and then by similar triangles. So this is kind of how I thought about it. So we want to show U equals U prime. So yeah, I'll just spend a couple more minutes writing this out before I move on to the next one. So we have PHU prime is similar to AJK. And PKU double prime is similar to BLH. And so basically we want to show that PU prime equals PU double prime. So here's what I wrote out. So I see you wrote in the chat. Hold on just a second. So I have PU prime over HP is equal to KJ over AJ, and I have PU double prime over KP is equal to HL over BL. And so, so we have those two ratios. And then, so PU prime equals PU double prime. Let me put these all on one line just to save room. And so we have PU prime is equal to PU double prime if and only if that second one is true. Okay, so yeah, so that's how we end up getting to that point.
Okay. So we have this because let's say triangle PLH.
Okay.
PLH is similar to triangle CLB.
Okay, so BLH is similar to CLB.
Yeah.
So yeah, so that's kind of like what Melik was saying. So yeah, so you're going to try to prove BLH is similar to CLB, right?
Yeah, yeah.
So angle CLB, and I'll just say by an angle chase, just because I don't think it's that hard of an angle chase, right? And so then, yeah, just a couple minutes. I'm just going to finish writing this up a little bit. So BLH is similar to CLB. Well, wait, is that true? CLB? Is that the right triangle? BLH and CLB?
Yes, that is the right triangle. BLH and CLB, yeah.
That doesn't seem true, because like...
No, it is true, because angle CLB is 90 degree plus a half of CPB, right?
CPB.
Yeah.
Yeah.
And
CLP.
CPB.
I'm sorry, I put CLB here. That's why I got confused. Yeah, you're right.
No, that's CLB.
Oh, really?
Yeah.
No, I think it's P.
PLH.
Oh, PLH and CLB.
Yeah.
Okay. There we go. Yeah, those look like they're similar. So then that means that PH over LH is BC over BL. Yeah, and that proves it. So basically, PH over LH is BC over BL. BC over BL. And similarly, we have PK over JK is equal to AB, or I'm sorry, AD over AJ, and we have AD is equal to BC. So combining the above gives what we want. So, all right, so we're really close to being done. So yeah, I skipped this angle chase just because I don't think it's that hard, but yeah, I guess I want to move on to the next problem soon. So this proves that PU prime equals PU double prime, which implies that U prime equals U double prime equals, we'll just call it U. And so so that means that P is the orthocenter. How did I do this? So, oh yeah. So that means that P is the orthocenter of A1ZU. Well, I forgot what I did here, but I remembered. So Oh, that just means they're orthologic. CID and HPK are orthologic. And once we know that, that means that, so that, I mean, that basically solves the problem. So the perpendicular from O to HK so CID and HPK. So the perpendicular from O to HK.
I think it is perpendicular from I to HK.
I to HK.
And yeah, and from C to PK.
C to PK.
Yeah, and from D to PH is contour. Yeah.
That means that OI is perpendicular to HK.
Yeah.
All right, this is a fun one. Yeah, sorry, I got a little messy because there was just so much stuff, and but yeah, I really like this solution a lot. Thanks, everyone. So let's see, there we go. All right. So yeah, orthologic. So we have triangle CID and HPK. So we draw the perpendiculars from C to PK, I to HP, or basically we draw the perpendiculars from each vertex in this triangle to the side of this